Welcome to Mojo community meeting. This is the fourth meeting. As usual, we have an exciting agenda. And our first presenter is Maxim, who will talk about implementing flat buffers in Mojo. Maxim, all yours.
Yeah, thank you. Just a second, I'll find my app for presentations. I guess you can see my screen now, right? I hope with a presentation. I can see you, so
yep,
vocal confirmation will be great. Yeah, thank you. All right, cool. Okay, so welcome to my talk. It's called Flat Buffers Mojo. So what we see here is a Flat Buffers logo and Mojo logo, and together they make really lots of sense. I think like the proportion is actually much nicer now with Mojo inside of Flat Buffers. Right. So like the first question is why did I started to create a Flat Buffers Mojo port? Generally, it's a little bit early. Mojo is a little bit early in the development, and things still change. So I'm Flat Buffers contributor actually, and I creating Flat Buffers for Mojo was anyways on my plan, but I thought to do it a little bit later. But then in the previous last month's presentation, Samay talked about his project, and it's called Mojo Data, and he wants to create a home for all kind of structured data processing in Mojo, and one of the points is Apache Arrow. And Apache Arrow is a data serialization format for tabular data, but like the metadata is actually represented through flat buffers. So in order to have like a nice possibility to port Apache Arrow to Mojo, it would be nice to have flat buffers Mojo support already. This is why we talked, and I said like, okay, let's maybe try to do it already now and see how it goes. Right. For folks who are not interested in generally in Mojo data, but would like to know what flat buffers is all about, flat buffers is a project hosted by Google, was implemented by Google employees or ex-Google employees, and now it's already, I think, over 10 years old. And as we in Mojo community are very performance focused, here is a benchmark which shows that with flat buffers, we have here following things to say, like we would like to decode, traverse, and dialog 1 million times, and it would take only 80 milliseconds in flat buffers and 302 seconds in protocol buffers light. And if you would use the C++ library rapid JSON, it would take 583. So like these numbers are quite show quite a big difference. So here we have a breakdown to actually understand what is going on. Why is flat buffers so much faster? Here we have a breakdown in decode, traverse, and dialog. And we can see that there is no time spent on decode and dialog and flat buffers. And traverse takes like this 80 milliseconds, where in protocol buffers, traverse is not that much slower, but there is lots of time spent in decoding and deallocation. Same with JSON, basically, right? So like decoding and deallocation afterwards take lots of time. We can see here that encoding is also much faster, but like the next row is actually quite interesting to see that why protocol buffers is so popular, and why we can't switch all the things to flat buffers. In a way, protocol buffers, what it does, if you have a object graph which you want to serialize, it's also encodes things and does some bit packing techniques, where in flat buffers, it's actually everything is aligned, so we don't need to decode. But you can see here the payloads are then bigger in flat buffers, and protocol buffers is mainly used for like transit on the wire, and there the payload size is quite important because we would like to reduce the time we spend in the network in the networking. Fun fact: Apache Arrow actually also use protocol buffers, so it uses flat buffers to define its schema and metadata about the table when it's stored on disk or sent as a message in IPC. Inter-process communication, but if you want to send from node to node, then there is actually another protocol where you would use protocol buffers to send stuff over the wire. Okay, so let me give a small example, like how it actually works.
So Maxim, can I ask you one simple question? So I've seen protocol buffers in TensorFlow, and I've seen flat buffers in TF-Lite, for example. So flat buffers are way better for performance, as you say, but people still keep using protocol buffers. So why? Is it
historical reasons, right? So like basically, like again, like protocol buffers was developed at Google, I think 2004 or something. Like flat buffers came only in 2010, and it came actually from their initiative in game development to help game developers to like use Google's like frameworks and so on and so forth. So like flat buffers still has this stigma of it's more for game development than for everything else, where protocol buffers is more known because of like networking, right? And then people just also use it for other stuff, right? So like, yeah, I guess mainly, yeah. From technical point of view, I would say if a payload is very important, then go for protocol buffers. If efficiency is actually more important and you need random access, then go for flat buffers. This would be like my 5 seconds pitch in a way. All right, so what we see here is basically just a simple schema where we define, like in flat buffers, like the class object, whatever is called a table. So we have a table person, which has a name, a string, and the age is an int. And then we say like, okay, the root type of a ballot is a person. So basically this buffer will be just this one person object, and this is it. Then what we can do, we can call, let's see, person FBS. This is like the name of the file with a schema, and then dash dash Mojo. This is what I'm working on. So like basically, let's see is a flat buffers compiler written in C++, and I'm adding Mojo support to it, mainly Mojo code generator. And then we get something like this. So we say like, okay, we get automatically generated file where we import the flat buffers, which this is just a small library which I wrote. It's like under 300 lines of code, which does like the infrastructural, like reading some stuff. It has just basically a few functions, helper functions. And then the structs themselves are quite simple. As you can see, you have a buffer and you have a position. This is where we see that we don't do the decoding up front. So basically, the only thing that we get is basically we say like, okay, there is a buffer, and this is the position where this specific table starts. And when we will need a name, then we will actually just look it up directly and get a string ref. Again, string ref, we don't even allocate a anything on the memory because we know we already have the data in the buffer. So we'll just give you a pointer, and the data in the buffer is also zero terminated and memory aligned. So there is no need for kind of like juggling with data and decoding and so on and so forth. And also there is no need for deallocation or, right. So like this struct could be just purely on stack, right? So like generally, and it is possible in flat buffers to have like all the traversal potentially just on the stack, and there would be no need to allocate transient memory and for heap allocations and so on and so forth.
Yeah, I mean, that's a huge benefit. That's one of the reasons why protocol buffers are pretty slow, is that they make like C++
Yes.
SD maps and all this stuff just in case you want to use it. So
yes,
keep
yes.
everything nicely M mapped in and things like this is huge.
Mm-hmm. So with flat buffers, you can also have this kind of like complete like eager deserialization. It's called object API, but this you normally do if you say like, okay, I would like to have nice API, or I would like to like do some stuff maybe multiple time. But again, like this is the default way of using flat buffers through this kind of structs, which are just pointers, which will be able to like load data at the runtime. And as you can see here, we have a static method. We say like, okay, this person give me this one as root, and you just give me a buffer, and then I will give you a person. There's also a static method to build the person. I wouldn't go into details in this. So like here is an example, basically a small test where you can see like, okay, we create a builder. We say person build with builder, name Maxim, age 43, then finish this buffer. We get a result, which is a tuple with a buffer and a size. We unpack it, we print it, and then we say like, okay, now we will create a person from this buffer. Again, as we know, we don't do any decoding. We just kind of have like a pointer to the buffer and a position where we need to start to read, and then assert equals person name Maxim, person age 43. So things works. Like here, we printed the buffer. What you can see directly, everything is memory aligned. For example, here's the UTF-8 encoded Maxim with zero termination and even padding, so that everything is aligned to 4 bytes. Here is the length, again, 4 byte aligned, and so on and so forth. Right. So generally, if you are interested, this is where currently this is the fork where I work on flat C, so like the code generator. And this is the flat buffers Mojo library, which does a little bit of infrastructure code. And I also have a few samples there, and I will add more samples when it's when I progress with the port. This is it from me. Do we have any questions?
Okay.
This is super cool, Maxim.
Thank you.
Yes, this is very interesting. Thank you. Okay, we'll now move to the second presentation by Martin. Please share your screen and tell us about Forge tools.
Hi, sorry, I was muted. Can you guys see my screen already? Or not?
There is echo.
echo in the sense of audio, or?
No, I'll select my. Can you hear me all right?
Yeah, that sounds way better, and can see your screen as well.
Okay. So I have quite a bit to go through, but please do interrupt and ask questions if you have any. What I've been working on is mainly two big projects, which are the array type and the datetime package. Datetime I'll leave until last because I think it's just a nice to have and not really a necessity, so to speak, right now in the point that Mojo is at. I just wanted to use it as an excuse to learn the language and build something cool. But yeah, array is mainly only for numeric types. It's Python also has an array, but it's not really used at all. Like you normally just use NumPy. But my idea was to add something like this to have, say you want to have just a short amount of numbers and you want to do, I don't know, dot product, you want to check if something is in the array, you want to do just some basic stuff like this APIs here that I'm showing. Bit of things like dot product, then you get the contains, multiplication, subtraction, sum, average, max, min, just some basic stuff with numbers. Also checking for if something exists in what index it's at, reversing the array, and just mapping functions, filtering, or applying a function with a where clause. Just some basic stuff like that. Why did I do this? I also wanted to show some benchmarks I did a while ago. Just a bit on the specs of the machine I'm using. It's just something on the low end nowadays, but it works. The sizes I tried were 3, 8, 16, 32, 64, 128, and 256. This is a bit of cheating because I wanted to show like what array is good at. You can also specify like a non-power of 2 array. It uses a SIMD vector underneath. It just rounds up to nearest power of 2. So it loses some performance when you're using, I don't know, 30 instead of 32, of course, because you're wasting some dimensions and you also have to pad and like mask those things.
When you do operations, is it doing like a SIMD of 256 elements, or are you using array and going through it?
Depending on what the SIMD bit width of the host is, but mainly it's pure SIMD operations.
Okay, so you use the bit width of the host. Cool.
Yeah, and if it's bigger than the, I don't know, it's kind of a rule of thumb, but I made it so that if it's bigger than a rule of thumb, then it just slices the vector in 2 and it operates in 2.
That makes sense. LLVM gets very grumpy if you say like, here's a 1,000,000 element SIMD, go load and do stuff.
I imagine.
Bad thing. It will do it, but it's not very fast. So yeah, sorry.
Yeah, allocation wise, you allocate the whole thing, but when you iterate through it, yeah, I cut it according to the host size, the SIMD width. But yeah, some of the operations that it can do, I wanted to show them side by side. I used inline array and list as a comparison point. And then you got array here. Most operations are actually quite similar in the speed. Only contains is really faster here in this graph for SIMD as for just pointers. What I was amazed by as I did these benchmarks though is how good list holds up against inline array, because I thought this was 100% on the stack and that just fetching from a memory would be much slower, but it actually holds up pretty well. And a weakness here is the index lookup for arrays is slower than for pointers. So yeah, that's something.
I mean, it may just be that the size of the size you're dealing with just fits in your L1 cache, and so it doesn't matter if it's on the stack versus one level in production. That could be.
Yeah, I didn't think about that. Yeah, but it's hard to compare as well because if you're, I mean, the maximum array size right now is 256 exactly, so you can't really compare 512 or I don't know 1024, right? So you would start seeing the difference from then onwards. I mean, right?
Well, I'm just speculating that just from a machine level, being on your stack versus being one on the heap, but still in your cache either way is probably going to give you similar performance. I'd speculate. I have no idea. I haven't measured. I haven't looked at your code, obviously.
Yeah, but that's likely. Yeah. And the second category, I just called it numeric operations. The big weakness here, sore thumb, it's filter. Filter, because it's a sequential operation and you access per index in the SIMD vector, and that's just very slow, it turns out. And every other category, it's actually faster than list or inline array, which was cool to see. But filter is pretty slow, and even here, the first attempts I did with pure SIMD sequential access were actually much slower, like 10 times slower each one of these. Right here, what I did to make it a bit faster is to actually allocate a pointer, send the SIMD to the pointer, and do the calculation sequentially with the pointer, and it turned out to be faster than using SIMD for the filter operations, like for the appending of the results. Anyway, this is like the biggest weakness of array. And where it actually shines is in vector operations, like reversing a list, doing dot product or cross product is just incredibly fast in SIMD. Like, it doesn't even compare. So anyway, these are just some quick benchmarks I threw together. If anyone has any suggestions, I'm open. Like, I did it like 1,000 times dot product, 1,000 times reverse, just for each different array sizes. But this can be developed further. Sorry, yeah.
Yeah. So one thing I'd love to see us build out more as the trait system matures and things is separating the algorithms from the data structures. And so at some point we'll define a collection type that is your inline array, that the off stack array, that the small vector type thing, that these things can all be composed into, and then have collections be orthogonal from the storage. And I think that'd be a really cool way to be able to, I mean, this is what the STL does in C++, for example, right? I mean, it's not a novel concept, but by doing that, we can have a pile of algorithms that are, that then can be applied for different use cases. And that way you can decide on a set of storage for your algorithm or your application, and then have the algorithms be consistent and specialized for different use cases.
That's awesome. That would be awesome.
Yeah, I don't know, Joe, did you want to add anything? Or are you just in +1?
Yeah, just agreeing with you. Right now, we just need to do several things along the way, like improved iterator support, before we can do algorithms. But yeah, we'll get there.
Yeah, exactly.
Anyway, this is it on the side of array. So yeah. Then the second thing I wanted to show a bit that we've actually already talked a bit on the PR, but is the result type, which is just the front end of the result type is basically the same as optional. It can either have a value or it cannot. And what's extra about result for people that are familiar with this data structure is that you have errors. So you can also check if the result is not there, you know there's an error, so it prints the error message that's in the error. You can also do things like choosing different types of errors and handling them differently. This is what I added to the PR, but I actually wanted to show a bit extra some ideas I've been having. This, well, of course, sorry, going back to result is you can just return a result when it's not successful, and the error message gets transmitted to the other result type, because the result is bound to here, for example, to type A, but this function returns a result of type T. And so here is just basically some constructor that takes in a result of a different type, but just copies the error and takes it with it. And you can also do stuff like this, like returning a tuple, like Golang style, just with a new type of error. Or you can retransmit the error that you received from this other function. There's just some ease of use capabilities. Anyway, getting on. The other idea I had is to have some kind of parametric error where we have some kind, like some fixed pseudotype, subtype, I don't know how to call it, for error, where, for example, in Python, it's pretty often used, you make aliases like for a specific error message, and you call it like value error, index error, but you're trying to build up pseudotype actually. So if we have this information at compile time, we could theoretically also add some other things I'll mention later. But yeah, basically when you check for an error, you check the if the error is set, and if the kind is the same as the value you're comparing it against. Or I just added the any error, which would be basically like a joker. It fits anywhere. Then you get to what this allows is to specify what kind of errors you return in the function signature itself. So it's to me, it's a pretty nice to have, which is like this function.
It's kind of like a new type almost, but within the result family or something.
Yeah, it's kind of like subtyping. It's pretty weird but interesting. And you can specify like a dynamic error message, but the kind is always fixed and known at compile time. And so we could do stuff like, for example, you have to deal with every error that can result from this function, for example, like Rust does at compile time. If you return a different error to another kind, for example, and you return directly A, which is a result of type int and index error, and you want this other error, just the error message gets transferred, for example. But if you print an error, it prints with its error kind, just like Python does, but actually it's not a kind really. And so you can expand this and add several types of errors that can return from the same result. And that way you have something like this. You have a function that can return more than one type of error, and you can do some kind of pattern matching against it. And like I said, if you know this at compile time, then theoretically we could enforce that every kind of error is matched against, which is something that is pretty powerful, in my opinion, about Rust. So we could, like, by default, that result always has an any error, and that any error always has to be matched, for example, after getting an error result. Just in terms of enforcing good practices, I don't know how to call it, just an idea. And on the language side, I had a bit of a crazy idea. Basically, I know we need in the future some way to unpack a variadic list. So, and in the future, of course, with the, the thingy Python syntax. But we also would need, I think, a way to embed a type in the parameterized definition of another type. I don't know if this sounds too crazy, but it's an idea I had. I would like to receive a variadic list, for example, for the error types, and be able to insert that into several error types. Not one type with the variadic list, but each with its own unpacked thing inside.
So within Mojo, there's a variety of type transformations that are just kind of hard-coded, hacked into it to enable certain things. Jeff, do you happen to know if we have the ability to implement type maps and things like this yet, or are we missing things?
The ability to implement them, I'm not sure, but the syntax actually would be like probably Python list comprehensions, right? You do error subscript, error for error in errors, and that generates you a list of types. So that's going to be the syntax for this variadic list embed. Whether we have the ability to implement this yet, I don't think so. I think that we're a couple steps away from doing something like this. But I agree, it would be pretty cool, and that we should build it.
Yeah, and this is one of the things, Martin, where we've put a lot of the machinery in there, because at the compile time metaprogramming phase, like types are just values, and so a lot of that plumbing's there, but I don't know that we have all the machinery to be able to transform types and apply them and things like this, so that you can actually build those functions at the bottom. But this would be very cool. If you look in the code in the Serum library, you'll see variadic pack and things like that are very very fancy in tuple, and like these things do some amount of this type transformation logic to be able to implement the type list coming into a tuple and unpacking it into an MLR type and things like this. So that's a little bit janky and hard coded right now, but we should totally generalize that over time.
Okay,
Yeah, I
cool.
think some of the
Good to
things you
know.
want to look for are like kgen.pack.load and then like git as kgen pack. If you look in built-in lists, you'll see some fancy things happening there.
Yeah.
Cool. Okay, I'll read it later. Now, other thoughts are going the direction of how do we interrupt with raising functions with this result type. The first idea I had is basically a new dunder method that gets automatically executed when the type gets assigned to a variable inside of a raising context. I don't know if this makes much sense to you, but this way there's no type that gets special treatment from the compiler. Like we don't say result has to be unwrapped when inside a raising context. We just define a new dunder method that gets always called when a type has it, for example. Like you call a do something that returns a result, and it gets automatically unwrapped because it is in a raising context. And this gets added by CodeGen. The other idea was just less magic, like adding an unwrap and wrap method and having to call that instead of a raising function. But the big problem with this is what I see is that in the future there will be several standards, and some libraries will return results and other will just raise, and users will get confused, and us in the standard library will have to decide just one way of dealing with errors. So this can lead to some fragmentation, I think.
But suggestion on syntax, you could use just the 2 square brackets, open close get item would be very short and terse here. And I think would match with a lot of kind of the expected syntax for like optional as well. Or no, optional uses something different, but kind of like reference and pointer.
So you mean like dereffing, like open close bracket?
Yeah.
Yeah, so I mean, I think there's really 2 questions here, right? One is the syntax you use, and do you call it unwrap or square brackets like Jeff's suggesting or whatever. Orthogonal of that, so syntax, orthogonal of that is behavior. Like, does it trap when it's not present, or does it raise? That's another thing, right? And then another question that you brought up was, do we want functions, I mean, outside specific domains, but like, is the general best practice to use raising or to use result types, right? And these are all kind of separate. On the last one, I think that I'd strongly suggest we stick with raises. We don't have syntax yet for type throws, but we have, Jeff, do we have all the machinery there? Is it a plumbing thing, or is it, we just haven't wired it?
We're like, I mean, it's a just go build it kind of thing at this point, realistically. I think that the last open question was, what do we do with try except? But I think that a lot of recent moving things around have made that quite easy to implement. And so, yeah, it really is like a just go implement it kind of thing.
Yeah, so anyways, regardless of the priority there, we want to have type throws in the language, of course. And so that I think is a big deal. And once you have that, then you're removing the like result is more powerful right now because you can specify the throw type. And so once you have type throws, you make result and raises be the same expressive power, right? And once you do that, then I think we'd really want to advise libraries in general to be using the raising and the language keywords and stuff like that for consistency and ease of use, and it dovetails with error handling and like all the good things that happen. And then we need to figure out like unwrapping and what is the best way to do that. Follow the Rust standard, for example. What do we think about for forcing an optional, forcing a result, and how do we keep those consistent and all that kind of stuff?
The other thing is that the sort of raise and accept are slightly more efficient than like a result type that may pack the 2 types together, because you don't have to move things around. And so you to be able to support non-movable types in non-movable result types with functions that raise versus a result, I imagine you'd have to like move things in and out of it.
Do you want to unpack that a little bit, Jeff, and also talk about named result types for folks aren't, or named result slots?
Oh, well, there's still haven't added the syntax for that because there's some, well, we can talk about this later, but there's something about the lexer and the grammar. But underneath the hood, when you have a function that raises, it actually gets the ABI actually gets two pointers, two different pointers, one pointer for the normal result of the function, and then one pointer for the error. And so what this actually means is that the functions that throw the result destination can be passed down all the way from where it was requested originally. From the chain of function calls, it's passing a pointer down to write the destination into. And the same thing is true for the error. So actually you can, when we have type throws, you can define a non-movable error type. And what a non-movable error type really means is you can raise one, but then not rethrow it. Not sure how useful that is, but what it really means is that when you propagate an error up the call stack, it's not being moved up the call stack. It gets written directly into wherever it's getting caught because that pointer is being passed down. And so that way the normal result type of the function doesn't have to be movable, which is great because we have non-movable types as part of the language. And it also means that when you rethrow an error, it actually just, the function just keeps returning. It doesn't even need to call a move function and, I don't know, copy 8 or 16 bytes around. So it's quite efficient to pass these two pointers down.
Yeah, and so this is also solving. I mean, this is very low level compiler internal detail, but this solves a huge amount of pain in the C++, NRVO, and in the Rust. Like everything's movable, and therefore you get mem copies everywhere, kind of domain. And so, which defining this away is actually a pretty big deal, even though it's something that nobody should ever have to worry about. Why does result not compose into that, Jeff? If you just return it and you don't throw, wouldn't that be the same? It seems like you've just constructed in place with the right thing.
Well, you mean
I'd say return result instead of throw or raise.
Well, result would get written into a destination, but then if let's say this function returns result int and one error type, and then you have a result that returns int and a different error type. And so when you have to move the int from one result into another because they're different types.
I see. Yeah. Okay.
When Chris mentioned named results, there was a proposal from quite a long time ago. I think it was almost like the month or two after we announced Mojo by Nick Smith, who has been a quite active member of the community and has influenced a lot of things, a lot of aspects of the language design where in place of like C++ kind of guaranteed named result value optimization, you can add in the syntax proposals, you give the actual destination of the function output and name that you can place directly into it, for example. So we've implemented this feature. It's just that the syntax has not been added yet. And so when we add it, we'll put it in the changelog and people can use it. And it's very good for being efficient. And the same thing is true for the error slide. You can write directly into the error and so forth. So this is kind of how you can access the low-level ABI bits of a function to be more efficient. For the error slot, it's a bit more of an arcane use case, but for the regular result of a function, there are many cases where you want to place directly into it, just kind of how the function is defined.
I'll see if I can dig up that issue number, but yeah, we should probably get going. I don't know, Tatiana, are we on track?
Yes, no, we are not on track. I don't think we are a little bit past a lot of time.
Okay, can I just zoom through the end? 5 minutes. I'll just
mine
zoom
is not
through
very
the
long,
rest.
so I probably need like 10-15 minutes.
Okay, then 5 minutes I think it will be, or not. Okay, I'll just zoom through. Basically, I also did a bit more esoteric math things like quaternions, which are pretty cool to implement. I mean, it's pretty simple code if you think about it, but the math was a bit harder to understand. But hey, it works. Also did dual quaternion because why not? Which is basically just using 4 quaternions in an 8-dimensional CMD vector instead of 4. But you just anyway when you're multiplying it, you have to divide the dual and the real part of the number and just basically do the multiplication in joining the vectors. Pretty simple stuff in the sense of how the code looks, not the math. But anyway, the datetime package is, I think it's somewhat ready to be used. I mean, I did quite a bit of testing, but the philosophy of the design is completely different to Python's datetime. I mean, most of the APIs are there, but I never quite liked the decision that they made, which is separate what date and time delta is, because it's just one coordinate system and everything spins around the sun. It doesn't make sense to separate them. Even our time is not really absolute. I mean, time, the seconds that we count them according to how much an electron spins around a silicon atom, but then we change the definition to use the speed of light. It's like it's never been constant at all. We just think it's constant, but yeah. And the way our days are counted is actually not exact as well. We have the International Atomic Clock Association, which just tracks the way the speed at which the planet rotates, which is also not constant. So we need to add leap seconds now and then, etc., etc. And Python takes none of this into account. So you get sometimes you get errors in date and time, and you end up having to install an external datetime library, which is often the case. And I've also I work as a data engineer in a company, and I've had quite a bit of pain dealing with time zones with datetime as well. I don't know which version they added support for IANA time zones, but it was pretty recent. And up until then, people had to code up their own datetime saving schedules and such. This is all integrated into this package. I mean, you can define your own datetime transition zones. You can define your own calendar. Actually, Python assumes you use Gregorian calendar. If you got lunar calendar or whatever, I actually haven't implemented to check if the abstractions hold up, but it's pretty solid what it did, because you have even the amount of milliseconds that a day can last is actually parameterized in calendar. So, for example, the other day I read that they're thinking about making a new calendar for lunar stations, because the day there lasts, I think it was 4 milliseconds shorter than normal Earth Day. And so I was quite ecstatic when I read that, because I actually take that into account in the algorithms here. They take into account what calendar you're using. You can also use UTC calendar, which is also something pretty classic that people assume will be there, but Python doesn't have it. Like, you have some sort of interaction with the UTC, but you can't build a calendar from the ground up with UTC in Python, for example. Like, and integrate it. Like, you can, this is, I used basically dependency injection. Like, you can inject what calendar you want to use, what time zone you want to use. You can specify what your time zone is like, what rules of transition for daylight saving time, etc., etc. And both date and datetime are recursive in the way that they calculate dates. And so I also built a fast package, which is more similar to what operating systems use for keeping track of time, which is basically just, especially datetime 64 and 32, which is just one buffer and you count the seconds since UTC. Basically, that's it. And you also have, I also built a lot of hashing, big endian style. Like, you can filter later on date and datetime. You can build your own database index or whatever with the hash, and you can fit these into 64 bits, 32 bits, or 16 or 8 bits. But these ones have lower resolutions.
Okay.
But yeah,
so at this time,
that's it.
I apologize, but I have to interrupt because we are very badly out of time. So thank you so much. This was very interesting. If anybody has questions, let's move this to Discord, and I'll give time to Jeff to talk about generics.
Yeah, sure. Thanks a lot.
Thank you so much.
I don't know if this actually opening the window makes it worse. Okay. So this is a quick presentation. It's kind of like just a quick recap of what's been happening with Mojo Generics so far, and a bit of a peek into the future, because there haven't been a lot of movement on this front, at least in the past couple of months. There are major movements. So kind of a recap is trace were introduced at ModCon late last year. So they're about maybe 6-7 months old. And another major thing that was implicit conformance was added early this year. So a trait is really, you can define an interface and say that my struct defines these methods. And we have trait inheritance that allows you to compose traits together, add more requirements to them, but you need to give it a name. So kind of the previous North Star that drove the initial implementation of traits in the language was, one is we want to be able to build generic collections like list, dictionary, and et cetera, that will actually properly move and destroy their element types. We also wanted to be able to define basic Pythonic methods like stir, length, and print over arbitrary types. Previously, they were hard-coded to only work on very specific standard library types, or you had to write, dunder line out yourself. And inheritance was introduced really as an easy stopgap for the language not having anonymous compositions. So, list now we're on collection element version 4 or something, but hopefully in the future we replace that with like and syntax or whatever to make it a bit more appealing. We had a couple of interesting things that happened along the way. For example, Chris accidentally introduced support for conditional conformances when strengthening parameter inference on self types. So this is pretty big, and there's been a lot of recent improvements in the quote unquote feature. That means it's a little bit less interesting syntax wise to define functions that support conditional conformance. I don't know if the syntax below will 100% work all the time, but I think the idea is that it would work. So this is pretty huge because when we drop traits, the first thing people asked for was implicit conformance. Okay, fine. We gave out implicit conformance because it was very useful. It's a much more lower friction bar of entry for those kind of basic Python methods. You just define a stir method and it works with a stir function. And then the next thing immediately after that was asked for was conditional conformances. So this is really big because it means that we can reduce kind of the set of requirements on the element type of list and other collections, but then still define richer methods over these collections based on the traits that the element type conforms to. It's kind of been the biggest use case of conditional conformances so far. And the major question here is what is the actual next North Star for generics? And really, it's up to you guys. It's up to the community, standard library contributors, and what the standard library is going to go for over the next couple of months. But I'll call out a couple of things that can speculate based on what people have been saying. One is going to be associated types or aliases in Mojo parlance. And I think that this is going to be really important for building out kind of iterators or ranges and other kinds of generic algorithms, because you want to say, I have a collection trait that has an element type. I have an iterator trait that has an element type that it dereferences to. And so and then this would kind of form the basis of any kind of generic algorithms that we would build.
So wouldn't this be more of associated values, not associated types? Because you should be able to use ints and anything here.
Yes, that's why I call them associated aliases. I don't know what the name we want to pick is, associated alias, associated values. We can call it associated values. Right.
Regardless of what y'all decide to name the thing, right? But it is more general than types, right?
Correct. You can have integers, you can have basically anything, right? Because we can have anything as parameter values.
That should more or less drop out. I think that because the V tables just have slots in them that hold comp time values, this is just another value that gets put in the same slot, right?
Yeah.
To be a function.
Yep. So it should all just work. We're pretty close to being able to implement this. There's a couple of more interesting wrinkles around here, but especially making the inference work really well. And also when it comes to inheritance, there's some problems that arise, but we're not too far away from being able to build something like this. Kind of the obvious counterpart to this are parametric traits. So in Rust, there's this common convertible from trait. And a couple of other very important base level traits in Rust are parametric. Parametric traits are nice because they're really kind of anonymous or slightly semi-anonymous composition of requirements. Convertible from is a pretty common one, which is how Rust is one of the way Rust does implicit conversions. There's a proposal out there for Mojo as well to do implicit conversions in the fullness of time with a trait like this. And then this begs the obvious question of like, what is the relationship between parametric traits and associated aliases? I don't remember the details. The last time I dug into this, one is not exactly a complete superset of the other one. So parametric traits feel like they could do everything associated aliases does, but there's one or two things that associated values have over parametric traits. And so this is kind of an open question at the moment, and I haven't really dug deep into it.
Yeah, I mean, my old battle axe of a language person feedback on this is that parametric traits get very complicated sometimes, because you can now you can conform to the same trait multiple times with different parameters conceptually, or you have to decide, can you conform to the same trait multiple times with different parameters?
So what's convertible from, the answer is yes, you're convertible from, int.
Well, let's separate from that specific thing, because that's also like very dubious for lots of different reasons, and extensions are probably a better solution for that. And it's like there's a whole bunch of stuff there, but so people often ask for parameterized traits because they want to be able to write the trait with some element instead of having to write where clauses and stuff like this. And so I mean, one of the questions is when do we tackle where clauses and all those pieces as well, because that is a very general, it enables a lot of expression as well.
Yeah. So open question, but it's
yeah. Well, it's a great question. It's a very important
something to explore as well. The other thing that might be coming soon actually is trait downcasting. So right now, if you have an any type, it's only ever going to be an any type. The syntax for the actual downcasting isn't here, and some people have asked that if I know that it is a subclass, that it is automatically retyped, but we'll have to see about that one, because that's not kind of behavior that naturally falls out.
Be a pattern match, and then a parameter match.
Yeah, Chris's never-ending love for pattern matching. We could do something like that. Is subclass is actually the right thing here, because you want to check that the meta type is a subclass of the trait type. And so we can kind of explain how the type hierarchies and meta type hierarchies work here one day, but we can also debate what the right is. Instance like x comma stringable might not be the right, is not actually the right syntax, because x is not an instance of stringable, it's an instance of, well, whatever the original type was. But then you would be able to write like print and, with an any type, and then you kind of can, parameter if your way down a couple of cases, and then maybe have an else that does a generic thing like oops, I don't know what this is, maybe just print its address if it has one, something like that. And so this will enable like a lot more, much more powerful generic programming going forward. And then a quick call out of like what else is on the table. So existentials are actually sorting this problem out in terms of the underlying kind of compiler and language infrastructure gets us quite close to existentials. And the other reason why they're very important is because we mentioned in the last meeting that Python interop, or calling Mojo from Python, is something that is underway, and it's going to be very important for boxing Mojo types into Python, right? Because you want to instantiate like a destructor, a move, a copy, and then pass those function pointers around. Box the object and then move it into a Python object. Another thing on the table is where clauses, perhaps supporting like a limited set of symbolic operations, probably just integers and in type methods. Extensions are also something that we can start building. So basic whenever it's necessary, but is really the more complex use cases of extensions that are interesting. So and those are a lot more involved in terms of like how they work, how we're going to implement them. But kind of like I just want to add a method to a type that's defined in someone else's package. That's something that is easy to build, but the more complicated generic programming stuff is maybe we want to hold off a bit on that. And then it's like, did I forget anything? But as far as
what's your thought on linear types?
Oh, right. Yeah, linear types are a thing. In case I don't remember if I shared that proposal yet, actually. I think I still haven't addressed some of the feedback.
Yeah, sorry, what do you want to explain what these things are?
Yeah, so I'll be very brief. A linear type is a type that doesn't have a destructor. which is profound because in Mojo, all types have destructors, and a linear type specifically doesn't have one. And what this means is it will force the user to actually explicitly consume values of this type. And this is very useful. For example, in Python, a common thing that you will see in almost every Python 101 is like, don't forget to close your file, right? Or, use a with statement so it gets managed automatically by the context manager. And what we can do is we can make file descriptor a linear type, so it doesn't automatically destroy itself. And it will go, hey, the compiler will actually say, hey, file descriptor is a linear type. I can't destroy it, right? But you could call the close method, which consumes the file descriptor. And then that was like, that's basically a reminder. It's like, oh, you forgot to, the compiler will enforce that you close the file descriptor essentially, either with a with statement or by inserting the call explicitly. And Veil has linear types, and Evan Ovandia, the developer for that, has written a lot, very passionate about this feature, has written a lot of blogs, and there's a lot of interesting patterns you can do with linear types. Like you can kind of grab a token and then exchange the token with a map to do certain things, and provides allows you to build like very strong API guarantees around types, because it allows an API to say, hey, like you have to use a type in a particular way. And enforce that through the compiler. So it's quite powerful.
I mean, one of the most simple examples is like you have a coroutine returned by an async function. You can just say like, you have to await this, which is just such a simple thing. And it defines away tons of bugs. And anyways, a goal here is not hard code stuff like that into the compiler. It's allow type authors to be able to express this for their demands.
Yeah. What you could totally do is you go through like any C++ or even Java like API doc, and then when you read, oh, it is an error to forget to call this method, it's like, okay, cool, make this a linear type, right? And you'll find tons of these throughout, like a lot of async or concurrency libraries will have a lot of, it's like you have to wait the task, you can't let it overhang kind of thing.
Yeah. So that's something that's plausible in the next, I don't know, month or two, or do you think that's? I think it's a straightforward extension to what we have.
Proposal and actually send that out is one thing that
that'd be great.
But we any questions?
Okay.
Perfect.
There were, Tatiana, you had a number of questions in the doc. Do you want to do lightning round on some of those?
Yes, I'd like to do. Let me share my screen. Okay. Okay. Let me actually skip to more technical ones very quickly. Okay. Actually, let's start from the first one. Is there a roadmap for supporting Python colon to Mojo modules? It would be very useful for Python-based companies that want to migrate large Python code bases progressively.
Yeah, it should happen in the next 3 months, or start happening in the next 3 months.
Yes, so that's the short answer. Okay.
You can share a more specific roadmap or something, but yeah.
Yeah, this is like the next big feature. So
yep. I'm not sure the next one is actually a question. That seems to be just a comment. Okay, next question. When is C++ interoperability expected to be available? By interoperability, I mean being able to import a C++ Clang module and use it directly like Swift offers. Perhaps sometimes this year, or is this a multi-year project? In particular, I'd love to be able to write an Himalaya-based compiler in Mojo.
I mean, I would give a order of magnitude early next year. Maybe we could start looking into this. This is something that so Mojo C++ interoperability, Mojo's type system is very compatible with C++, and so there's a ton that we could do here. But on the other hand, C++ is itself a gigantic mess. Tying into Clang is a bunch of investment we'd have to do, and given all the other things going on, I think that it's probably not the big thing for us to work on for a while. We have a whole bunch of C++ code that we're migrating to Mojo, and so it would be really awesome for Modular as well.
There's a lot of low-hanging fruit we can do that doesn't involve opening the Clang box. I think that is a lot much like lower risk and easier, like higher return on investment. Like opening up Clang and being able to directly import a header file is a much more involved kind of project.
I mean, it's a project, but I mean, between projects, we're prioritizing that first one, making it so Python teams can progressively move to Mojo because that's higher impact. But what I'd say is that so Nick, who friend but not able to be here because of time zones, there's C bindings, right? And so MLIR has C bindings, and so what we use for a bunch of stuff is we use the C bindings for MLIR, and so you should be able to actually use that kind of stuff. And so it's kind of annoying, but you're not actively blocked if your goal is to write MLIR-based compilers in Mojo.
Just be careful with dilibs because their MLR dilibs are a bit of a struggle.
Yeah.
Okay. Next one, is the type pointer here to stay as a low-level tool, or are there plans to deprecate it in favor of unsafe pointer with conditional conformance methods?
Maybe Joe, do you want to?
Sure. Yeah, I'm happy to talk about that. We actually have Daniel that's actively working to remove D-type pointers. So just the other day, we finally got back and removed legacy pointer, the old pointer. And so now we're back down to 2 pointers, and D-type pointer is on its way out the door. There are a lot of PRs happening right now to get us back down to just 1 pointer type.
And so is that
to answer your question, yes, there will be conditional conformance methods for like the strided load, strided gather, etc. The things that only make sense for a SIMD aware pointer, if you will.
Cool.
Okay.
What happens to capital reference? Have y'all made a decision about the naming of that?
No decisions yet, but I know that we'll have to figure that out soon. Notably, reference carries a lifetime, pointer does not. I know that you would like to rename reference to pointer, but we still need to figure that out. Let's get through one round of the release where we remove pointer, and then we'll revisit.
Just to overshare, unsafe pointer is a good thing, and we need that in our repertoire. That's very important. We have capital R reference that is actually a pointer. It's just a safe pointer. And so one path we could take is rename reference to just pointer, and then you have unsafe pointer and you have just pointer, and you have the 2 duals. One carries a lifetime and is but it's still explicitly dereferenceable, just like pointer is, and things like this. And so
this is going to be really important because a lot of data structures expose an unsafe pointer like API, which is a bit of a foot gun that people have noticed. And so these things are really just return a pointer that has the same lifetime as the collection. By the way, deleting legacy pointer is huge.
A huge thing. So legacy pointer is never trade aware. So
yeah, to give you an idea, I probably imagine that I'll land somewhere in that 24.6 where we have the duals that you're talking about, Chris. So I'd like to upgrade a lot of our APIs that are taking like pointer length to work in terms of reference. Have basically all of the public APIs be working on this reference type before we solidify on the names.
Cool.
Okay.
So let the round of removal go in at 24.5, and then we'll target the final endpoint in .6 probably.
I am thrilled with everybody's work to improve the standard library. It's huge, and it's a lot of work.
The goal is to make it simpler for everyone, easier to reason about.
Okay. Next one, if people know, IFMI MAD-MAC instructions used when doing with SIMD vector product reduce set.
I think so. You could go look at the implementation, but I believe so.
I'll take it offline. I'll double check what's there and answer here. Samay, how much effort would it take to support JSect, CSect template style tags like the code which is shown here? So
can you share your screen?
I'm sharing.
All right. Is it me?
Can people see my screen?
Oh, no, it is me. It is a me problem. Zoom changed their UI, and now I'm super confused about this kind of stuff. Sorry about that. I think this would have to be extremely motivated by some kind of use case. This is like a very are you trying to like go for a React style kind of I don't know what you call React, a framework? Like, is the goal here some kind of like React style framework in terms of like web dev or, you know, being able to generate HTML?
Yeah, same as an idea, but for example, we can run a macro like using that kind of syntax with header tags and stuff, and then it transforms it into HTML. So I don't think we have something similar like this at the moment.
Sounds like a research project.
Yeah.
So, I mean, this is one of the fun things of having a strong comp time deal is that you could probably get into string parsing and it would be fine, if not probably really slow at compile time, but it would be worth exploring.
Not unrelated, but there are other things that are pressuring Mojo to improve the performance of its compile time interpreter. So, you know, maybe it'll be faster.
Yeah. Yeah.
Okay. And the last question is, what are plans for Mojo self-hosting?
I mean, so this gets into, there is no plan. I mean, I can give you at best like some crazy ideas. Right now, we're really focusing on build out and mature the language, the library, and learn and go. Chris's crazy idea, which this is definitely not a team opinion, but I would love to rewrite the parser in Mojo at some point. So, you know, this would be a next year thing at the earliest, but that'll be profound. And I mean, I think that would be very, very cool for a variety of reasons. I don't know if Jeff or other people would be happy about, you know, is Laszlo going to be grumpy about rewriting MLIR entirely in Mojo? Probably that would be a thing too far, but you know.
So I think that when our compiler stack matures, we should definitely think about baking it. And this is for performance reasons. And when we bake it, it's basically a rewrite. And at that point, I think we could rewrite it in Mojo.
Yeah.
And maybe take a lot of lessons learned from MLIR, I guess. But that to me is a bit further away.
This is all very blue sky. This is not a plan. So someday, yeah, and by the way, MLIR could be way better. Just it's a good thing, but it could be way, way, way better if
You've also learned a lot in terms of building a language on top of MLIR. And it's like kind of the requirements Mojo has for a compiler infrastructure go beyond perhaps what MLIR is capable or willing to provide. And so by doing it again, we have the opportunity to like fix a lot of problems with kind of the way the language is implemented.
Yeah, but I mean, the flip side of that is that in the absence of having like actually make it super easy for Python packages to be formed from Mojo and like these other things, even C++ interop may or may not be a critical thing to invest in. But something would be amazing to do, but it's very blue sky at this point.
Yep. Okay, I think these are all the questions. Thank you so much for answering, Chris, Jeff, Jack, Joe.
Awesome. It's good to see y'all.
Well done. Thank you. Bye.